So today is my topic. Topic name, if I say, so the topic is very simple topic, but it has a proper, the importance here. The topic name is AMI, which is a electromagnetic induction. Okay. So electromagnetic induction. So my problem is here. So how can I induce induce means like example for suppose I am saying that how can I actually now generate a EMF, induce an EMF in the particular coil, right? So first of all, what I wanted to do is a flux. So first I wanted to always remember that there is a magnetic flux is the important concept for us. So what is a magnetic flux is that, so B into B dot B bar cross A bar, right? Which is I can write it as a BA cos theta. But if I have a number of turns in the coil, so number of turns in the coil, if I say, so then this formula will become as a flux is equal to NBA cos theta, right? So what do you mean by this flux? Flux is nothing but, so if I say, so in saying I can say that the number of this is a coil, through this one that now magnetic field is passing through this one in this manner. Now how the coil is actually oriented is important. So the coil orientation is always important. Now the coil is in this manner. If I draw a normal to it, so this is the area of the coil. If I draw a normal to it, this is the phase where it is pointed, means the coil which direction it is pointed. It is very very important, right? So now in this case, what is that here? For example, this is the area. So the pointing of this coil is in what direction? To the normal to it. So for example, the coil is little bit tilted in this manner. So the magnetic field is still like this only. The magnetic field is like that, but the coil is actually pointed. The normal of the coil is actually pointed in this manner. So what I'll do is here, if I say this is actually the area multiplied with a unit vector, we call it as an area vector. So it is making an angle with the theta. Though the what is it here? Basically, the number of field lines will actually changes here. So whenever it is changing its orientation, the flux will automatically changes. So this theta is actually, this is the angle between, if I say angle between what is it here, the coil and the magnetic field. Okay, this is a basic concept I am actually discussing. Then if I say, for example, now if I wanted to show you something like that, so logically if I show one important point, how an EMF is induced. EMF is induced whenever I say, now according to the Faraday's law. So Faraday's law, what is it here? So he is actually says that the magnitude of EMF is equals to what is it here? The change in flux divided by change in time, but the number of turns. So here important is that this term is about a single coil. Okay, the single coil. So inside the single coil, now the number of turns will changes now. Definitely EMF will be induced. Obviously, now obviously what is the condition I would like to do is here. So the flux, whenever I talk about a flux, flux is depending what is that number of turns in the coil, the magnetic field and the area and the angle between them. Anything if changes. Now area, this if I wanted to change a flux, either you can change the angle, you can change the area, you can change the magnetic field or number of turns. In all the cases, what is it here? The EMF will be generated. Simple here. So whenever I change the turns here, EMF will be induced. Field will be changed, EMF is induced. Area change, EMF induced. Cos theta changes, EMF induced. Here itself I can show you that the number of turns, magnetic field, area and the angle between them is changes. The flux automatically changes. Due to that, what happens? EMF will be induced. Okay, this is a basic thing. We know already that. So there is one more person called as a lenz. Lenz also very very important person, where he is actually able to tell that the certain things, like for example, if a magnet is trying to pass from a coil, like this one coil is there. So the magnet, if I wanted to pass this from this particular coil, this coil automatically develops certain thing, certain some pole called as north pole here, and the back side is south pole. It will develop. So there is an anti-clockwise current will be developed. This current is actually an induced current. What is this one here? Induced current. Why it is developed like this now? So this whenever this EMF is there, this EMF is actually negative of what is at here in terms of flux, change in flux divided by change in time. So whenever the magnet trying to reach towards the coil, automatically what is at here, this EMF is induced, but this EMF is actually opposite direction. This EMF is actually developed in opposite direction. So what is the induced current here? Induced current is what here, EMF divided by what is at here, the resistance of the coil. So EMF is actually what is it, N divided by what is that here, R, and now I can write that d flux divided by dt. There is one case is very important. What is that case is now? Now this particular current, whenever this induced current is there, whenever this induced current is generated in opposite direction, means it will not try to allow this this magnet through the coil. Reason is this is if you like to go away from it, then automatically now this magnet if tries to go away from it, then what happens here, automatically here, like for example, now I'll take this is the north pole, here a south pole. So here automatically what happens here, south direction current will be developed, which means it is not trying to now, if I try to analysis if I try to do, now this magnet whenever it trying to reach towards the coil, north pole of the magnet, and this is with the velocity v, here north pole is developed. Okay, but whenever this magnet is actually going away from this one, so what is that happen here, automatically inside this coil, that this coil has a change in its current, means it will be clockwise current it will develop, here it will be anti-clockwise current. Why it is like that now? Reason is simple. This is called as a, here we call it as electrical inertia. Okay, electrical inertia. Okay, electrical inertia, which is nothing but what is that here, that is a we can call it as a inductance, you can call it as a inductance L, that will be developed. So what happens here, whenever you are trying to go, it will oppose, whenever trying to go away from it, then also it will oppose. So both the situation, what is that here, it is also here, who is that it will oppose, here also it will oppose. So both the cases, what is that, this will, the content will try to oppose, means the induced current try to oppose. So this is given by whom here, Lenz. Okay, so Lenz has provided the direction that EMF is equal to N divided by d flux divided by dt. So now I will come to the actual point. So this Lenz law is actually important. So Lenz law is important in showing the direction. Okay, showing the direction of a current. Okay, obviously showing the direction of current, but it is most important. Okay, if I say this is most important in showing the polarity. Okay, showing the polarity of what is that here, polarity of EMF, which is that induced EMF. Okay, induced EMF, it will be important. Now this Lenz law is also important in a conservation of charge. So conservation of energy. So this fellow had one more thing also given, that is a conservation of energy. Reason is, now for example there is one a pipe is there. So this pipe whenever there is a magnet falls into it like this, the north pole is falling towards the south like this, automatically here also what happens, north pole will be in a anti-clockwise, now north pole will be develops here. So what happens, this pole whenever it falls here, now this is possessed with a potential energy which is a mgh. But whenever it passes like this, whenever it passes through this one, what is this will be like, this magnet whenever it tries to passes through this one, this potential energy converts. Okay, this will be converts into what is that here, electrical energy. What is this here, electrical energy. Again what happens here, whenever this reaches the magnet, reaches the ground, automatically this electrical energy again converts into Joule's heating effect. Okay, so Joule's heating effect, okay, it will develop as a Joule's heating effect and it will disappear or dissipate, right? That is a very important concept. Now I will talk about the important thing in a JE and JE NEET and JE mains and advanced question, as well as NEET questions will be important from this particular aspects. So what is it like, for example? So one particular question is that how a charge develops charge dependency. Okay, charge dependency we will try to speak here. What is a charge dependency? Like logically, now when there is a coil, basic coil or solenoid, whatever you take, like this here there is a coil here. So whenever the magnet is approaching towards it with velocity v, so magnet whenever it is approaching here, this is the north pole, it will develop, back side it will develop south pole. So automatically anti-clockwise current will be developed. I know that. So now if I try to show the charge dependency, just now we discussed I is equals to what is it, E divided by R. EMF is nothing but a minus N divided by R, change in flux divided by change in time. Now from this one I is equals to minus N divided by R times of change in flux divided by change in time, fine. But I is nothing but what is it, dq divided by dt, which is equal to minus N divided by R. Now change in flux divided by change in time. This time can I cancel? Now if I take it, total charge is equals to minus N divided by R times of. Now what is it here? There is a change in flux, means flux 2 minus flux 1. Right now, so basically this charge is independent. Okay, charge is independent of what is it here? Time. First is it is independent of time. Okay, secondary thing is that whenever the flux changes, the charge automatically induced, means here charge automatically, charge automatically tries to flow from higher potential to lower potential here, because somewhere we'll get some positive potential, somewhere we'll get a negative potential. Current is automatically flows through this, so some EMF is induced in the coil. Okay, some EMF is generated in the coil, so automatically some current is induced. So here the dependency of the charge is depending on what quantity, how it is depending, what it is depending, it's very important. Sometimes they will directly ask this question. Then secondary part I would like to ask, the motional EMF. Here my main concern is motional EMF. What is this motional EMF? Simple. Now I have to, before talking about a motional EMF, I have to talk about a Fleming's. Okay, Fleming's rule also I have to take it. The Fleming's rule. Fleming's rule is nothing but Fleming's right hand rule. I have to take it. Okay, right hand rule. So this right hand rule is nothing but this is like, for example, I will extend my fingers, right hand fingers I will extend. This may be a thumb of me, and this is like a forefinger. Okay, and this is a central finger, right? Central finger. Okay, central finger we have it. So thumb will always indicate the motion of the conductor. Motion of conductor. Main important that motion of the conductor as well as the direction of current also it will show. So just for an understanding, I will tell you, the forefinger is actually about a direction of a magnetic field, right? Magnetic field direction. The central finger is what is it here? Induced current it will show. Okay. So I will talk from this one. We will discuss about it. Then you might have studied that a left hand rule. Okay, what is the left hand rule? The left hand rule, the thumb if I show, this is a thumb if I show. Thumb indicates what is it? A magnetic force. And the remaining thing is that if a current is actually middle finger and forefinger is actually magnetic field. So same thing left, but F is actually magnetic force. Here is what is that here? Motion of the conductor. It is important. Now let me talk about a motional EMF. Very clearly we will discuss. It is like a model of question. Very important. Let's see. So I will talk about a basic question now. For example, there is a magnetic field in this manner. So this magnetic field in this manner, if it is there, right? So whenever there is a conductor, basically let's suppose there is one frame I am keeping here. Okay. So this frame, what is that here? For example, there is one length, one small length is there. This is the length. This length, it's trying to move in this direction with the velocity v. So what happens if I use my right hand thumb rule here? Magnetic field is actually inside. The direction of motion of this one is left side. So current will be in which direction? It will show like this. So there is this sort of induced current. This current is actually a generated current. Okay, induced current inside this coil. Why it is there now? Let's suppose. So here logically if I say, so this is if I bring it here, so every time what is that here, I am changing my area, right? For example, I told you flux can be changes whenever magnetic field changes, whenever number of turns will changes, whenever area changes, whenever angle between them also changes, then only flux will change. So now here I am talking about the area. Whenever area is changing, motional EMF will come. So definitely in this situation what I can consider, so EMF is equal to, I have a change in flux divided by change in time. So here if I say change in flux, here area, so B into area divided by, I can take it as dt. Next what is that here, d by dt of B. Now magnetic field was constant. Area is, let's suppose this is the length of this one is L, and this is the breadth I am taking here. So here length times of breadth, but you see length is actually constant, but change in breadth. So if you change the breadth here, what is that here? It will be a velocity. So that will be BLV. So this is the induced EMF BLV, but it is what is that, negative. Okay, always you have to maintain a negative. Okay, so okay, now EMF is actually negative, which is I got it as a BLV, right? Or else a BLV. So whenever there is a flux is changing, it will change that a BLV. Now my question is little bit complex and we'll try to do. Now second question what I'll do is here. For example, if there is a magnetic field in this manner, so this magnetic field, what is this one here? For example I am taking here because this is my main topic here. So whenever this magnetic field is, now I am taking one irregular shape of wire. Okay, the irregular shape of wire, and it is started from A point to B point, right? Now whenever it is moving, so the main important is that it is develops a EMF. We will go this direction, but now I have to take a effective length. This wire now it will behave as, I have to take a effective length. The effective length is what is it? EL effective. I have to consider this is almost equal to 1 cell, because you see whenever it is moving in direction, the current is induced inside this one is like this. So what happened here? One important point I would like to discuss here. See, so what is it now? For example, as I speak about this point, my question is, this is like this one wire is moving, right? This is A and this is, let's say, B, moving in this direction. This wire is behaves as a, now we have to take its effective length, L effective length, which is nothing but A to B effective length. This will be almost equal to what is that here? SL. Cell with the internal resistance, EMF is E, EMF is actually BLV. Got it? So even though if it is a irregular shape, the EMF will be what is it? A BLV. So effective length always we can find it as a B times of a L effective times of what is it here? A B. This is a shortcut we have to follow, because if we consider any other thing, it will be cancelled. Okay. Other thing, like for example, there is one more question I would like to discuss. Now, for example, like this. What is this question is? Now there is a wire in this manner. This is A point and this is a B point. They will ask you calculate a positive potential, which is a positive potential, okay, on the wire. Okay, what is the positive potential now? I have to follow always what is that here? Shortest path. So which is L effective is actually equal to what is it here? AB. That's all. Now which direction? Let's suppose if it is moving in this direction, by using the right hand timings rule, the current will be in this direction. So now the cell, it will be like this one, it will be like a resistance, the cell. So now what is it? This is the EMF, this is will be BLV. But which is a positive potential here? The A will be having a positive potential, and the other terminal B, whatever you are taking, which is a B, will be what is that here? A negative potential. Right. Now let me do little bit advanced level now. What is it now? For example, there is a, I am taking one of the frame here. Okay, here one more frame. Like this, there is a frame which is situated inside a magnetic field. These are all important. These are all important. These are all very, very important. Right? Now there is one. Let me say there is a. For example, I am taking here one of the resistance R. Here R1. Here what is it? Here resistance is R2. There is what is it? A question is actually this rods are sliding on it with the velocity v, velocity v, velocity v, like that. Some velocity they are taken, and now this rod is actually moving. Now our question is very clear. So this graph will become what is that by using the right hand rule. This is the induced current here. This is the induced current here. Right? So now here already this is the resistance R1. Then what is it here? Next is R2. Resistance R2. Now this one is a cell, but the cell is actually like this. Okay. This term is actually like this. The current inside this one is in this manner. Here also the cell is actually what is it here? Like this. The current inside this one is what is it here? Like this. Okay. I current will be flowing in here. So like that you have to consider. Now it becomes a circuit diagram. You have to solve. So simple what is it here? And now you see this and this what is it? This is R1. This is the R2. So from this one we have to calculate. So this is the internal resistance of the rod R1. This is the internal resistance of R2. This is R1. This is R2. Next what is it here? So this will be converted into what is it now? So you see this is a cell here, and this is the R1 plus R2. Okay. Next this is one, the connection whatever we have. So here whatever the connection is there, then what is it here? So this is the R2, and then R1. So you have to take it as R2 plus R1, and there is one more cell. This will become like that. Next, one more question I will take it here. This model is very, very important. For example, there is one. This is recent advanced question. There is one frame was there like this. Now this frame is connected with the capacitor. Okay, this is under what is it here? This is under the magnetic field. Okay, now here one rod is actually sliding in this direction, moving with velocity v. So here the induced current is I. So what happens? This is a capacitor. What is this one here? It is a capacitor. The current is actually induced in this manner. So now this circuit will convert into, now this is a one capacitor, obviously. Now what is this one here? The current is actually induced in this manner by using the right hand Fleming's rule. So here it becomes cell, the internal resistance like this. So this is the R internal resistance, this is EMF. EMF is actually BLV, right? And this is the current which will follow. Now whenever it passes here, the charge on this one is Q. This will be positive charge. Automatically it will develop a positive Q, and here it will be negative charge, it will develop, and this is what a circuit. Now how much charge will be there? Charge is equal to what is it here? C times of E. So C into E is nothing but what is it here? BLB. This is one equation I can consider. Right? So now one more simple logic I will take, because now there is a hybrid questions also possible here. So how much force it will experience? Like you see, whenever the conductor is moving in this direction with velocity, then the magnetic force will act here, and this one is this direction, which is a force is nothing but what is it here? BIL. This is Bill sin theta, right? But Bill 90 degrees here, so force is equal to what is it here? BIL. It will become. So now what is the force it will experience? Then I have to do this question. So this charge is not if I change with respect to time, because if you are changing then what happens? C into B into L into change in velocity divided by change in time. So what happens here? This will become current. Current is equal to what is it here? C B L into what is the change in velocity with respect to time is nothing but acceleration, right? So now what happens here? This force is equal to what is that? I can write a CBL, right? CBLA of A, and here there is a B already there, L already there. Now it becomes what is that here? B square C L square times of E. That is your magnetic force will experience by the what is that here? Yeah, the this particular rod, the capacitor charge. So different questions can be possible. Like for example, there is one more important question I will discuss. Now possible that I'm taking like this. Okay. Now there is a this also advanced level. So what is that here? For example, this is one plane. So on this one rod is actually sliding like this, right? So whenever it is sliding downward direction, the magnetic field is acting on this one is this manner. So whenever it is sliding down, let me say and something is sliding down direction, its weight is actually what is it here? Mg. Now what happens here? It makes an angle how much here? Theta. So you know already this will making angle how much here? Theta. So this will be mg cos theta, and this will be what is it here? Mg cos theta. This will be what is it here? Mg sin theta. So that this direction what I'll have here mg sin theta because magnetic field. Now this sliding right, this direction force will be there, that is a magnetic force. But magnetic force is actually what is it here? It will be equal to BIL. It will be like this. So now whenever it is sliding here, so whenever it is sliding down direction, you see it will slide with an acceleration what is it here. So now I use here mechanics question. So mechanics I can use it. So what is the mechanics here? So magnetic force downward, left direction. Let's say what is it here? Mg cos theta downward direction sin theta, which is equal to mass into acceleration. I can consider. Or else, if you know the sign convention properly, so this is left direction, this is right direction. So I am taking this is also right direction acceleration m into a. Why? Because summation of fx is equal to what is that here? M into a I can consider right now. So this is nothing but what is that here? Minus BIL plus mg sin theta, and then what is that here? Mass into acceleration. Now anything else you want to add up here, like acceleration or any formula you want to add, you can actually add it here. Now obviously here also we know that EMF is actually equal to what is it here? BLV. EMF is actually what is it here? BLV. Now this is also possible here. So you want to add like EMF in terms of current, or you want to add, you can do it. Like for example, I is equal to what is it? E divided by R times. So E is actually what is it here? BLV divided by R times I can add. So this term I can take it. Now for example, in terms of the current is removed, I can replace with this one. This will become a little bit complex equation. So you will get it that point. So this sort of questions are possible in the motional EMF. And there is also like one more question. I would like to discuss this question and conclude. Now for example, there is this is very important. The rotational part. Now for example, one rod is actually rotating. This also comes under the rotational motion with an angular velocity of how much here? Omega. So here there is like for example, this is a magnetic field which is uh, like this into the plane. So magnetic field is actually what is it here? Into the plane with the omega. Now what I'll do here, one of the small element is actually having a velocity in this direction, which is the dx. So now EMF, now small EMF d is equals to what I can write, magnetic field, so no changes. L is actually the dx. V is actually I'm writing V only. So let me write one more thing, B dx. B is nothing but omega times of what is it here? R, but I will write it as a, so it is located from the center to this length is actual x length it is located. So I will write omega times of x. So here a small EMF. So if I integrate on the both the side, EMF is equal to what is it here? B times of omega integration of x dx. So what is it? And if you are doing it from 0 to total length, EMF will be equal to what is it here? Half times of B omega L square. This is a rotational EMF. What do you call this one? This name is actually a rotational EMF. So in a rotational EMF, let me discuss the content. There is possibility that there are certain questions are there. Like for example, there is a famous question that there are the number of spokes are there here, like this. Okay, like this, so many spokes are there of the tire which is revolving in the magnetic field. So revolving in the magnetic field like that. So whenever it is revolving in the magnetic field, so here what happens? So whenever it is revolving in the magnetic field, logically let's understand. There is one rod if it is revolving like this omega. Now it is revolving like this with the velocity v. Then it looks like to me that is a here it will be a small resistance and there is one cell will be there. There is a current I will be passing like that. Now you see everything is connected to from the axial to the ring. So this entire thing will be converted as your combination of cell with a small resistance. Likewise, right? So many resistors are there, so many cells are there, but they are all parallel combination. So E effective will be equal to what is it here? They are all parallel combination. Then what is it here? That will be equal to individual EMF, which will be equal to half into B times of omega times of L square. This is the length of the spoke. So even though they might give a 100 scope, 200 scope, 100 scope, so it doesn't mean that how much EMF it will generate. It will able to generate only this much, right? So there are the possibility that you can actually change angle also. You can do anything here, but here possibility that whenever it is revolving, you have to take the important concept here. Now, for example, there is a one more little bit tedious question I will discuss. Now, the rod is actually there in this manner. This is a rod. This rod is actually revolving about this one in this manner. Now, it is revolving about this one axis like this. How much EMF is induced? Okay, guess what? How much EMF is induced? Now, do it. How do I do it? So, obviously, if it is making an angle theta, if it is making an angle theta, so whenever it is revolving, now what I have to do here, so the main important thing is that listen, so I am revolving in this manner, right? So one important concept I have to have in my hand, that I can divide its length. So like for example this length is there, now it is making an angle theta, I would divide like this, so it will be like L sin theta for me, and this will be like L cos theta for me. Now who is actually making a rotation like this? L sin theta. So that is what. So B is equal to half times of what is that here? B omega into what is that here? L effective. Here in this situation, L effective square is what is that here? Half times of B. L effective is what is that? L sin theta. That's it. Whole square. So you will get a rotational EMF for this sort of cases. So I hope you like this one. If you got any doubt, you can ask. Thank you.